everyone, welcome back to Markov processes. When we last left off, we were talking about the concept of recurrence and transience for states of a Markov chain. And the idea was for us to be able to get back to the conversation about whether or not a given chain has a limiting distribution and whether or not it's unique and whether or not it depends on the starting value of the chain. So you'll recall that a recurrent state is a state that we're going to keep returning to infinitely often. State I is recurrent if starting at I, you will return in finite time with probability 1. And by the Markov property, once you return to I, the past history is no longer important. You are now sort of starting over at state I, and you will return again with probability 1 to state I. So you're going to keep returning an infinite number of times. Whereas a transient state has an escape route. So starting at a transient state I, you may actually return several times, but eventually you're going to hit some path through the space of the chain that takes you away from ever being able to hit state I again. And in the last video, we actually computed the expected number of hits on a transient state I before escaping, never to return again. So for a recurrent state, by the way, it is possible to have a recurrent state that you can never hit in the first place. So the definition that you will return an infinite number of times is predicated on the fact that you start there. State I may be recurrent, but you may start the chain at some other part of the state space where you don't have communication, and you might never be able to reach I. That doesn't mean it's not recurrent. The definition of recurrence depends on you actually starting there before talking about returns. Okay, so we defined a probability. I called it lowercase g sub I last time. This was the probability of returning to state I in finite time, given that you start at state I. And this was how we defined recurrence. If a state is recurrent, then the g sub I for that state I is 1, you will return. And if it's transient, that g sub I is less than 1. But computing that probability is not always an easy thing to do. So for most of today's video, I want to talk about an alternative way to characterize states as being either recurrent or transient. And this characterization is going to depend on the probability P sub I super n. So that is the probability of going from I to I in n steps. And that is not necessarily for the first time. When we talk about P sub I super n, we have computed things like this in the past, and I do think it's easier to deal with than computing that probability G sub I. But going from I to I in n steps does not mean you weren't there in between. So I'll come back to that, but I want to start off by talking about a tool that's going to help us in proving the theorem that I'm going to state today. If you've taken mathematical statistics with me, you know that I'm a big fan of indicator functions. And if you've taken mathematical statistics from me, the indicator functions I'm going to use here are going to look a little different. They have the same idea. They are 1 or 0 based on whether or not something happens, but the notation may be a little bit different than how I use them in mathematical statistics. So let's define an indicator function. I'm going to let capital A be a set of real numbers, and I'm going to define an indicator function. I'm going to call it capital I sub capital A of x. This is a little x. This is an argument. In the world, you may see indicator functions defined with a capital I like this. You might see like a numeral 1 that's sort of double lined. You might see a kind of chi symbol. You might see special brackets known as an Iverson bracket. There's many ways to write down indicator functions. This is what I'm going to use here. And this indicator function is going to be defined to be 1 if this x is in A and 0 otherwise. Now, there's no randomness here, but we could consider, for example, this indicator function with a capital X plugged in, where capital X is a random variable. And that means that until you observe that random variable, the indicator function, you don't know whether it's going to be 0 or 1. So this indicator function with the random variable plugged in is itself a new random variable that takes potentially 2 values, 0 or 1. We're often going to look at a random event A. So this A is just a set of real numbers. But when you first take a first probability course, You usually define events with like a capital A, capital B, and capital C. For example, maybe you roll a fair six-sided die and you let capital A be the event that you get an even number. You then go on to talk about the probability that A occurs, things like that. So we're often going to look at a random event A and the indicator just I sub A, not of X. And we will define this to be one if the event A happens and zero otherwise. Again, this is a random variable if this is a random event. Now, as a specific example, this random event might be defined in terms of a random variable. I'm going to let X be a continuous random variable and consider the indicator. And then down here, this is a big subscript. I have some brackets and capital X being greater than 3. So this is the event that you observe your random variable to be greater than 3. And this is just an example of this with a specific event. This is defined to be 1 if capital X is greater than 3 and 0 if capital X is less than or equal to 3. So even though in my example X is continuous, this indicator random variable is a discrete random variable because it only takes on the values 0 and 1. And we're going to want to compute probabilities and expectations for this indicator. Let's look at the expected value of this indicator random variable, continuing this example. The expected value of the indicator that capital X is greater than 3. Again, the indicator takes on the values 0 and 1. We're going to get 0 times the probability. This is 0 plus 1 times the probability that this indicator is 1. The 0 part goes away. The 1 I don't have to write. This is just the probability that this indicator is 1. And this indicator is 1 if and only if the event being indicated happens, because that's how the indicator turns on and becomes 1. In other words, the event that the indicator that X is greater than 3 is 1 is equivalent to actually observing X greater than 3. So I can rewrite this probability as the probability that X is greater than 3. What we see here is always going to happen. The important thing to take away from this example is that the expected value of an indicator is always the probability of the event being indicated. Of course, assuming that we are using indicators with random variables. The expected value of an indicator involving random variables is the probability of the event being indicated. This statement is going to hold even in a conditional universe. So if this up here was a conditional expectation, the expected value of this indicator given that another random variable y is equal to 3, then this is going to be the probability that this event occurs in the conditional universe, or given that the random variable y is equal to 3. With that, we are ready to write down an alternative characterization for recurrent and transient states. I have a theorem for you, and that is that state I is recurrent if and only if the sum as n goes from 1 to infinity of p sub I super n is infinite. Alternatively, I is transient if and only if this sum is finite. Again, this p sub I super n is the probability of going from I to I in n steps, but it does not mean that the first return to I was in exactly n steps. So you might have visited I several times on your journey from I to I in n steps. And this, of course, means n time steps. We're going to sum as n goes from 1 to infinity. If you want to start with n equals 0, that is fine, because we would just be adding a single term here. Pii super 0 is the probability of going from I to I in 0 steps. That probability is always 1, because if you start at I and you take 0 time steps, you are still at I with probability 1. Adding a 1 to this sum is not going to affect whether or not it is infinite or finite. But I'm going to start it from 1. There's no need to add an extra term that we don't need. Okay, so to prove this, we can prove this in either case, right? This is an if and only if statement. So if we prove one of these, we're going to get the other one for free because if it's not recurrent, it's transient. If it's recurrent, the sum is infinite. If it's not recurrent, then the sum had better be finite. Otherwise, this theorem would be saying that it was recurrent. So we only need to prove one of these, and I am going to prove the transient case. I'm going to start a Markov chain at time 0 at some state I where I is transient. And I'm going to let capital N be the number of returns to state I at times greater than or equal to 1. So it's a number of returns, not a number of hits. So I'm not going to count that hit at time 0. If I is transient, we know this happens if and only if G sub I is less than 1. This was that probability from the last video. This is the probability we return in finite time to state I, given that we start at I. And the definition of transience is that this G sub I is less than 1. Now, G sub I is less than 1 if and only if the ratio G sub I over 1 minus G sub I is finite. And this ratio is the expected value of n given that x0 is I. You can see this in the last video. If you didn't watch that one and you want to know how I got this, please check out the previous video. So where are we now with this line? I'm going to write this sort of in a different order. I've got infinity strictly greater than the expected number of returns to state I, given that we start at I. So the next thing I'm going to do is rewrite this number of returns using indicators. I want to go down the chain at time 1, time 2, time 3, and say, did we hit I? Yes. Let me tally that. Did we not? Okay, ignore it. So I'm going to go through the chain and record like a 1 every time we hit I and a 0 otherwise, and add those zeros and ones. This is a great way to write down the total number of returns to state I. In other words, I'm going to replace n with a sum as n goes from 1 to infinity of the indicator that indicates whether or not the chain at time n is in state I. Again, this is going to pop out a 1 every time the chain hits state I and a 0 otherwise. And when you sum them, you'll get the total number of hits on state I, and we are only looking at times greater than or equal to 1. So here's where we are. And I am going to pull the sum outside of the expectation. To do this, I'm going to use something, I'm not going to actually justify it, but you could use something known as Fubini's theorem. I've already done a kind of thing like this in one of my previous videos for this course. I don't want us to get bogged down in too much of the analysis. So in this course, you don't have to justify these sorts of things. An expectation is a linear operator, so finite sums can always go in and out easily. Infinite sums, you have to be more careful, and you really should justify these things. But we're just going to pull it out. And when you pull it out, you have the expected value of an indicator in a conditional universe. And we know that the expected value of an indicator is always the probability of the event being indicated. So I can write this line as the sum as n goes from 1 to infinity of the probability that xn is equal to I, while staying in the conditional universe where x0 equals I. And this is the probability of going from I to I in n time steps. This is little p sub I super n. We've got that it's finite. This is what we were trying to show. And if you follow all these lines through, they do all apply in both directions. So we do have an if and only if here. If state I is transient, this sum is finite, and vice versa. If this sum is finite, state I is in fact transient. So super useful theorem for making a formal argument for recurrence or transience when you don't have a nice small state space where you could like start looking at sample paths and saying, oh, look, there's an escape route. The state is transient. This is a really useful theorem for establishing it when it's not so easy to just look at everything and figure it out sort of on paper. Okay, so I have another theorem for you, and that is that recurrence and transience are class properties. By class, I do mean the communication classes. And I've already maybe even stated this. We're going to prove it now. And I think I may have argued it for you. So let me remind you of what I mean by this. Suppose we have the state space consisting of states 1 through 5 and a transition matrix that looks like this. This is actually an example we've already seen in a previous video. We sort of walked our way through this and figured out that this Markov chain has three communication classes. We had a class consisting of states 1 and 4, a class consisting of state 3 alone, and a class consisting of 2 and 5. So, like if you look in closely at 2 and 5, and just these rows and these columns, you'll see that once you're at 2, you can only go to 2 or 5. And when you're at 5, you can only go to 2 or 5. So if you start at state 2 or 5, you are going to be in there spinning around between 2 or 5. You're never going to move to another part of the state space. And we have argued that 2 and 5, I don't know if it was this particular example, but in this sort of case, that these are going to be recurrent states. State 3 here is absorbing, so that is super recurrent. Starting at 3, you will always be at 3. The other states, 1 and 4, are transient, and here's why. Starting at 1, you can easily see that we can go to 2 or 5, and we don't have to do it in one step. But because we can do it in one step, we can easily see these are non-zero probabilities. So if you go from 1 to 2 or 5, you are then stuck in the class with 2 and 5. This makes state 1 transient, even though starting at 1, you can return to 1. And again, that escape from 1 does not have to be possible in one step. So maybe if this matrix were a little different and you can't go from 1 directly to 2 or 5, maybe you could go from 4 and then to 2 and 5. This would make state 1 transient. State 4 communicates with state 1. So I can tell you right now without really examining where a chain starting at state 4 can go, because they're in one communication class here. If I start at state 4, I know I can get to state 1 if we put together the communication classes correctly. And from 1, I know I can escape to this class over here, which means starting from state 4, there is a way that I will move away never to be able to return to state 4 again. So you can think of state 4 in that respect as sort of inheriting transience from state 1. Yes, we could have argued that state 4 was transient more directly, but you see that by virtue of it communicating with state 1 and state 1 being transient, state 4 is also transient. This is the idea behind this statement that recurrence and transience are class properties. But let's prove it. For proving it, I'm going to prove it in the recurrent case this time. And once that's proven, we are done. Because if I have a state I that is recurrent, and I say I communicates with J, and we prove that J must also be recurrent, then if I now start with state I being transient and say that I communicates with J, and I try to say that transience is not a class property, therefore J must be recurrent, but J communicates with I. And because we've proven that recurrence is a class property, that would have forced I to be recurrent and not, it couldn't have been transient. So we get the transience for free if we prove it in the recurrent case, or we get recurrence for free if we prove this theorem in the transient case. So we only need to prove one case. I'm going to do the recurrent case. I'm going to let I be a recurrent state and suppose that I communicates with J. We're going to use our new characterization for recurrence to show that J must be recurrent, and then we will have proven this theorem. We start with something recurrent, we have something it communicates with, and we're proving that that other thing must also be recurrent. What I want to show is, I'm going to use the theorem we just proved. So what I want to show is that the sum as n goes from 1 to infinity of the probability of going from J to J in n steps must be infinite. This is equivalent to saying that J is recurrent. Because I is recurrent, this sort of sum is infinite if you look at I. So the sum as n goes from 1 to infinity of the probability of going from I to I in n steps is infinite because we're assuming that I is recurrent. Now, because I communicates with J, this means that there exists some integer number of steps that we can go from I to J and from J to I with positive probabilities. I usually use n and m here, but I kind of want to reserve my n. So I'm going to say, because I communicates with J, This means that there exists an integer m and k greater than or equal to 0, such that we can go from I to j in m steps with positive probability, and we can go from j to I in k steps with positive probability. So check this out. Let's look at the probability of going from j to j in n plus m plus k steps. There may be many routes you can take here. I'm going to look at one particular route. So I'm going to look at a very specific case, and that specific case is going to happen with smaller or equal probability because so I'm going to put that this probability is greater than or equal to something because the something I'm going to look at is a very specific path, and there may be many more ways to go from j to j in n plus m plus k steps. So that's why I have an inequality here. I'm going to imagine going from j to I in the first k step, so that's real specific, and then from I to I in the next n steps, also real specific, and then from I to j in the remaining m steps. So this is like one kind of path you can take that is included in all the possible ways you can go from j to j in n plus m plus k steps. Again, that's why I get this inequality. So let's sum the left-hand side over n going from 1 to infinity. This is going to be greater than or equal to summing the right-hand side as n goes from 1 to infinity. And I'm going to pull out the things that don't depend on n, so we get this. Now, because I is recurrent, I do know that this sum is infinite, and I want to say this whole thing is infinite. I would have a problem if one of these two probabilities were equal to 0, but they're not because we specifically chose k and m so that both of these are strictly positive, and we get that this entire right-hand side is infinite, and that makes this left side, which is even larger, it also must be infinite. So we have proven that this sum is infinite, and maybe that's enough for you, but I'm going to reindex things to make it real clear. I'm going to rewrite this as the sum as n goes from m plus k plus 1 to infinity of p sub jj super n. So check it out. Up here, when I plug in n equals 1, the superscript is m plus k plus 1. Down here, when I plug in the first n, the superscript is m plus k plus 1. And match up the next one and convince yourself that these are the same exact sums. This is infinite. So if I want to start the sum at n equals 1, I can because probabilities are never negative. So I'm not going to take anything away from the sum. At best, it's going to get larger and still be infinite. In other words, the sum as n goes from 1 to infinity of the probability of going from j to j in n steps is infinite. And by the previous theorem, this means that j is recurrent. So we started this theorem or this proof with starting with the state I that is recurrent, and we assume that I communicated with j, and we have proven that j is recurrent. This means that recurrence is a class property. State I is recurrent. If it communicates with another state, that state must also be recurrent. And again, transience inherits the same thing. If I is transient and it communicates with j, and you don't think j is transient but recurrent, the fact that that j being recurrent communicates with I would contradict that I was transient to begin with. So we have proven the theorem, and it wasn't bad at all. And we used our new best way, I don't know about best, but a really useful way to characterize recurrent and transient states. Next up, we're going to talk about a super important example in stochastic processes, not only Markov chains. And this example is going to allow us to illustrate a lot of things, and we're going to revisit it many times in this course. So very important. And that is a random walk on integers. So what we're going to talk about is a very basic random walk. There are other flavors of more complicated random walks, but let's get into it. I'm going to start at any integer, positive or negative. For example, let's keep it simple and start with the integer 0. At each time step, we're going to create a chain walking through time. And at each time step, this chain is going to go up by 1 with some probability p, where p is a parameter between 0 and 1 inclusive, or it's going to go down by 1 with probability 1 minus p. So for this flavor of this random walk, there is no staying flat. If you start at 0 in the next time step, you cannot stay at 0. you'll either be at state 1 or state negative 1. And the assumption here is that these moves are all independent. So the next time step, you're going to go up by 1 with probability p or down by 1 with probability 1 minus p. And it has nothing to do with whether or not you went up or down in the previous time step. If this probability p is strictly between 0 and 1, and we're going to mostly stick to this because it's not that interesting to just go up, up, up deterministically or down, down, down. If it's strictly between 0 and 1, then all states communicate. In theory, it is possible to get anywhere from state 0 and to get from anywhere to state 0. It may not be easy, especially for extreme P's, but in theory, it is possible. So all states communicate. You're not going to get trapped into a part of the space where you get stuck. So if all states communicate, we say that the chain is irreducible and we have one communication class. And this means that all states are either recurrent or all states are transient. When all states of a chain are recurrent or transient like this, we say that the entire chain is recurrent or transient. I've never heard anyone use this kind of language where they say the entire chain is recurrent or transient without having an irreducible chain. Although I think in theory, you could probably have a reducible chain where all of those communication classes are maybe recurrent and technically the whole chain would be recurrent. But I've never heard the language used that way. So when we say a chain has a property, it usually implies that there was irreducibility, if that makes sense. Okay, so we want to figure out whether or not this random walk is recurrent or transient, and we only need to check one state, and then we'll have it for all states. So today we're going to check state 0, and we're going to use our new theorem. We want to check whether or not the sum as n goes from 1 to infinity of the probability of starting at 0 and returning to 0 in n time steps, whether this is infinite, in which case 0 would be recurrent, or finite, in which case 0 would be transient. And I know I keep saying this, but I want to drive home the point that going from 0 to 0 in n time steps, this probability here does not preclude us having visited 0 in between. Now, what do you think we're going to see here? Informally, if p is greater than 1/2, then that means we're more likely to go up than to go down. So starting at 0 or any state, I think this chain is going to kind of drift up and eventually be at some very, very large states. And it's going to be difficult for us to return to where we started. So I think intuitively, if p is greater than 1/2, I think we should expect to see that this chain is transient. If p is less than 1/2, I expect the same thing. It's going to drift downward. And I think we're going to see that in this case, this chain is transient. Now, if p equals 1/2, then we're going to have this balance where the chain sort of is equally likely to go up or down. And if we have any hope for recurrence, I think it's going to be right here. That said, if p is 1/2, you might have a few ups in a row. So maybe starting at 0, you find yourself at state 7. If p is 1/2, now you're going to find you're kind of hovering around 7, and it's difficult to come back down. There's a concept of recurrence where we're going to break it down further into sort of fast recurrence and slow recurrence. We're going to have different names for it. Stay tuned. Okay, so let's try to do this formally. I want to look at this sum. If it's infinite, we have recurrence. If it's finite, we have transience. So what do these probabilities look like? Starting from state 0, in the first move, you either go up to state 1 or down to state negative 1. There is no way to go from 0 to 0 in one time step. So the probability of going from 0 to 0, sort of super 1 in one time step, is always 0. Similarly, starting from 0, you could go up 1 and then back down. You could be at 0 at time 2. But any number of ups you do has to equal the number of downs you do. So we actually cannot go from 0 to 0 in any odd number of time steps. So P0, 0, super 3, super 5, etc. All of these probabilities are 0. So let's focus in on an even number of time steps now. And specifically, let's get started by talking about 2 time steps. What is the probability you go from 0 to 0 in 2 time steps? One of two things has to happen. You either go up and then down, or you go down and then up. And those two kinds of paths to return, those are disjoint events. You cannot go up in the first time step and down in the second time step while also going down in the first time step and up in the second time step. By disjointness, think Venn diagrams, we can break this probability up into a sum of two probabilities. Now, the probability of going up and then down, there is nothing about this random walk where the probabilities are dependent on time. So this is just going up and going down, and those moves are independent. We get to multiply the probability little p times the probability 1 minus p. Over here, we get 1 minus p times p. And you can add these. We get 2 times p times 1 minus p. More generally, when n equals 1, 2, 3 on up, let's look at the probability of going from 0 to 0 in 2n time steps. So we're hitting all the even numbers. If you return to 0 in 2n time steps, this means you have to have exactly n moves up and n moves down, not in order, not up, 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 and down, 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 down. But you have ups and downs, and you may hit 0 in between. But if you're going to be back at 0 after 2n time steps, you need exactly n ups and n downs. So we're going to get a p for every up and a 1 minus p for every down. So this probability is going to sort of look like p to the n, 1 minus p to the n. But we do need to take into account all the different ways that that can happen, just like we did when we went from 0 to 0 in 2 time steps. We didn't just get p and 1 minus p. We got that for 2 different types of paths. So we need to be able to count all the types of paths. The coefficient in front used to be 2 when we were looking at p0, 0, and 2 time steps. And now we have to say out of the 2n time steps, we have to choose n of those steps for going up or n for going down, and the rest will fall into place. So the coefficient here is going to be 2n choose n. And this is an expression for the probability of going from 0 to 0 into n time steps. Okay, so back to the task at hand, we want to compute the sum as n goes from 1 to infinity of p00 super n. Half of these terms are 0, so let's rewrite this as the sum as n goes from 1 to infinity of p00 super 2n. And we have an expression for this. It's 2n choose 2, p to the n, 1 minus p to the n. This sum is actually not all that fun. So I'm going to break out two tools here. We're going to use the limit comparison test from calculus, and I will remind you of what this is, and something known as Stirling's formula for n factorial. This combinatoric thing here involves factorials, and this Stirling's formula is going to be helpful because this is not something that we know how to sum. Okay, so as a reminder, the limit comparison test. If you consider two series, the sum over n of some an and the sum over n of some bn, and if your an coefficients here or terms here are greater than or equal to 0, and your bn's are strictly greater than 0 for all n, then we can define a constant c to be the limit as n goes to infinity of an over bn. Now, this limit could be 0, it could be infinite, but if it's in between, if c is strictly greater than 0 and strictly less than infinity, then the limit comparison test says that both of these series either converge or both diverge. And if we can determine convergence or divergence of one of them, we will know whether or not the other one converges or diverges. We won't know what the sum actually equals, but knowing convergence or divergence is exactly what we need to know for showing recurrence. We don't care, if the sum is finite, we don't actually care what the number is. So the limit comparison test is going to be the way we're going to tackle the difficult sum we have in front of us. And so this is from calculus, and I don't want to take the time to prove the limit comparison test here. So I'm sure you can find a proof in any calculus book for sure, or Google a proof. I don't like to send you away to do stuff like that, but this is not Markov processes. Okay, Stirling's formula. Stirling's formula says that n factorial, so it usually has a squiggly line like this, and I'm going to define what this means in a moment. It is not has the distribution, which is what we usually see in a probability course like this, but it's some sort of approximation. And it's not two squiggly lines because it has a very specific meaning. So I'll get back to that. But on the right side of this squiggly line, I'm going to put the square root of 2 pi n raised to the n plus 1 half and an e to the negative n. So in this context, this squiggly line means that if you take the ratio of, say, the left side to the right side or vice versa, and you take the limit as n goes to infinity, you get 1. So it's sort of a way of saying that both sides act the same asymptotically or in the limit. This is blowing up. If you take the limit of this side as n goes to infinity, it's blowing up. So is this, but they're sort of going at the same rate in the sense that the limit as n goes to infinity of this ratio is equal to 1. You prove Stirling's formula using something known as Wallace's formula, usually. Um, and this is something I would like to show you. I don't want to take time away from this course. So I do hope to come back and eventually make a video on the proof of Wallace's formula and Stirling's formula. It's not going to be my next video because I do want to keep forward momentum in this course, but one day I'll come back and link, and it may be sooner rather than later, but it's not my focus for the next video. I want to keep the course going, and when I find some time, I will do a whole video on proving Stirling's formula. For now, I'm going to ask you to believe it. And with the limit comparison test and Stirling's formula, we are ready to go back to the sum that we are trying to compute to show whether or not the random walk is recurrent or transient. So a coefficient in that sum was 2n choose 2. This is 2n factorial, quantity factorial over n factorial times n factorial. And this is asymptotically equivalent to, so I'm just using Stirling's formula in the numerator and denominator. Here you can see it directly. So this is filling in for n factorial. Here you can see it again. And up here is the same expression, but with two n's in place of all the n's. Now, this might take a moment to convince yourself of this cancellation, but it should cancel down. It does cancel down to 4 to the n over the square root of pi n, and this n is under the square root. So I am going to look at the two sums for the limit comparison test. I'm going to let a sub n be 2n, choose n, p to the n, 1 minus p to the n. This is exactly the thing we want to sum. And I'm going to let b sub n be, so I'm going to replace the coefficient with this one that's asymptotically equivalent, and then also put the p to the n, 1 minus p to the n. If I look at C from the limit comparison test, if I form the ratio here, the P parts are going to cancel. And then this and this are asymptotically equivalent, and this limit is going to be 1. So this value of C is strictly positive and strictly finite. The limit comparison test applies. Now, what we want to look at is the sum of the ANs. Instead, we're going to look at the sum of the BNs. If it's finite, then the sum of the ANs is finite, and we will have proven that state 0 is transient. Whereas if the sum of the BNs is infinite, then the sum of the ANs is infinite, and we will have proven that state 0 is recurrent. So let's look at the sum as n goes from 1 to infinity of b sub n. Here is b sub n. And let's see, I'm going to pull out some stuff here. I'm going to pull out, well, there's not much to pull out. I'm going to pull out 1 over the square root of pi at least, and I'm going to organize all these things with the n exponent together. And this is, I don't know what's going on here. It depends on the value of p. So I want to graph this for p, 1 minus p, for p between 0 and 1. We get a parabola that looks like this. It's tied down when p equals 0 or 1. 4p times 1 minus p is 0. And it takes its largest value when p is 1 half. And that's where we get 4p times 1 minus p equaling 1. So when p equals 1 half, this sum of the bn's is 1 over the square root of pi times the sum as n goes from 1 to infinity of 1 over the square root of n. And this sum diverges. The square root of n is less than or equal to n. So 1 over the square root of n is greater than or equal to 1 over n, the famous harmonic series. If you sum from 1 to infinity, 1 over n, that definitely diverges, and this is only larger. We get something infinite when p equals 1 half. And this corresponds to what we saw intuitively. when the probability of going up or down for your random walk is equal, then you don't sort of drift away. And this is where we get recurrence. So again, the sum of the bn's is infinite when p equals 1/2. By the limit comparison test, the sum of the an's is infinite. The sum of the an's is the sum of the probability of going from 0 to 0 in n steps. That is infinite. And we have proven that state 0 is recurrent when p equals 1/2. And because all states communicate, as long as p does not equal 0 or 1, the entire chain is recurrent. The entire random walk recurrent when p equals 1/2. Okay, so when p does not equal 1/2, then, well, let's just get out of the way. If p is 0, then this whole thing is 0, and this sum is finite, and everything is transient, although it's harder to talk about the entire chain as being transient because all states don't communicate then. But we can say that any given state is transient when p is 0 or p is 1. So let's focus on p not being 0, not being 1. So we do have communication. And let's ignore p equals 1/2 because we've already dealt with that. When p does not equal 1/2, and again, not 0 or 1, this 4p, 1 minus p, is less than 1. And the sum of the bn's is the sum of, so I'm going to call this 4p, 1 minus p, I'm going to call it r. And we get something that looks like this. So n here is, as n increases, it's only decreasing this summand. So this sum is less than or equal to the sum as n goes from 1 to infinity of r to the n. This is a nice geometric sum, especially because r is strictly less than 1 in magnitude or otherwise, because r is not negative. I know that this sums to r over 1 minus r, and r is between 0 and 1. This is finite. So when p does not equal 1/2, the sum of the bn's is finite. By the limit comparison test, the sum of the an's also finite. The an's were p00 super n. So we have just shown that when p is not equal to 1/2, the sum as n goes from 1 to infinity of p00 super n is finite, and therefore state 0 is transient. And in a case where p is not 0 or 1, all states communicate and the entire chain is transient, which is what we expected when we talked about this intuitively. And so to finish off today, I want to focus on the recurrent case. Suppose we're looking at this simple random walk on integers. There are other versions, for example, where you can stay flat or where you can jump more than one state at a time. But the simple random walk that we have defined here, let's stay in the recurrent case where p equals 1/2. In this case, the chain wants to sort of balance the ups and downs. But as I mentioned earlier, if the chain happens to get away from 0, so maybe you're running the chain by flipping a fair coin, heads, tails, 1/2, 1/2, up, down. You might get a string of heads in a row, in which case your chain has sort of climbed up above 0. And when it gets to some higher state or equivalently some lower state, the 1/2 up and down probabilities make the chain want to balance there. So it becomes difficult to get all the way back down to 0 where you may have started this chain. In fact, we are about to see, or I'm about to claim, that the expected number of steps to return to state 0 in the case where p is 1/2 and the chain is recurrent, the expected number of steps to return to 0 is infinite. Now, this may sound crazy to you because recurrent means we're going to return in finite time with probability 1. And I just told you that the expected time to return is actually infinite. Here's the difference. I'm going to let capital T be the first return time to state 0. And I do mean first return because so far today we've talked about returning in n steps, not precluding you having returned earlier. But now I want to talk about the first return. If the state is recurrent, we know that the probability that t is finite, given that you start at a particular state, so state 0 or any state I, let's say state 0, starting at 0, the probability that t is finite is 1. That's the definition of recurrence. Now, one way to compute this probability, not the only way, might be to write this as the sum as n goes from 1 to infinity and look at the probability the first return happened in one step, the first return happened in two steps, and so on. And those are distinct disjoint events because we are talking about a first return time. So returning in finite time, the first return being finite means it either happened in exactly one step or it happened in exactly two steps or exactly three steps. These are all disjoint events and we get to write it as a sum. And you may not want to use this sum to compute this probability, but it's one way to do it. So if t is the return time to state zero and zero is recurrent, this sum is finite. But what is the expected value of t, given that we're starting at zero? This would be the sum as n goes from 1 to infinity of n times this probability. And so, although it might not make sense intuitively, mathematically, you can see that it could be possible for this sum to be 1, and in particular finite, whereas this sum with the coefficients blowing things up actually not being finite. So mathematically, I think not so bad to see. Intuitively, I realize it feels weird to say I'm going to return in finite time with probability 1, but it's going to take an infinite expected number of steps. So again, mathematically, you can see that this coefficient blowing up could make that possible. And I claim, due to the chain wanting to balance, that if it moves away from state 0 or any other starting state, it's going to want to balance where it is later and we'll have a hard time returning. We proved it's recurrent when p equals 1/2. I claim that the expected number of steps to return is going to be infinite. So final thing for today, I have a definition for you where we're going to break down recurrence further. I'm going to let I be a recurrent state. If the expected number of steps starting from state I to return to I is finite, we say that I is positive recurrent. And otherwise, if the expected number of steps to return is infinite, we say that I is null recurrent. So positive recurrence is sort of this fast recurrence where the expected time to return is finite. Null recurrence, this kind of dragging out slow recurrence that we see, that I claim we're going to see in the random walk. I'm going to talk more about this next time. I'm going to finish up this random walk discussion for now, next time on Markov processes. I hope to see you there.